Hi everybody, I am going to do a short video where I'm going to talk about energy transitions of electrons from different shells and how to calculate the energy, the frequency, and the wavelength. So I'm just going to work it on some paper while you watch. Alright, so the first question, if you can read that, says, what is the energy of an electron on the second shell, or in the second shell? Well, energy is just equal to the Rydberg's constant, negative, divided by the shell squared. So in this case, it's just equal to negative, and the RH is just a constant. It's negative, the RH is a constant, 2.179. So negative 2.179 times 10 to the minus 18 joules is the R value. And then we just divide it by n squared, which in this case is 2 because we're in the second shell. So 2 squared, or 4. So if you do that calculation on the calculator, you get negative 5.448 times 10 to the minus 19 joules. That's the energy that an electron is if it's sitting in the second shell. It is negative, and you may remember from the lecture that actually all energies are negative, and the less negative it becomes, the closer to being out of the atom it is. So the closer, so 0 is when the electron is totally removed. Okay, what's the second? The second question here says, what is the change in energy for an electron that jumps from the fifth shell to the second shell? Well, there's a lot of ways that you can do that, and you can use the equation that we used up here, and you can say, well, we'll just take the energy of whatever shell we're starting in, we'll take whatever shell we're finishing in, final minus initial, and then subtract the energy of the level that we're ending up in. If you rearrange that equation, then you have a more useful way of finding it, and that is delta E equals, let's get that over here, negative RH times 1 over n final squared minus 1 over n initial squared. I think that's the easiest equation to use because it's straightforward. There's other ones that you can use, but I like using this one just because it's easy to plug it in. So what are we going to do? So our negative RH is just negative 2.179 times 10 to the minus 18 joules. And then the final shell is the second shell, so that's 1 over 4, 2 squared. And then the initial is the fifth shell, so that's 1 over 5 squared, or 25. So that is what we have. Now, your book goes through a lot of trouble, I think, by trying to find a least common denominator, and which in this case would have to be 100, and then multiplying both sides. It's just going to be a number in the end. So in my opinion, I just think if you calculate these numbers, you're going to be good. So I would just say, well, that's equal to negative 2.179 times 10 to the minus 18 joules. 1 divided by 4 is 0.25. 1 divided by 25 is 0.004. Just do that subtraction. So that's going to equal negative 2.179 times 10 to the minus 18 joules. And it's 0.246. So my final answer will be negative 5.360 times 10 to the minus 19 joules. That's how much energy of an energy change there will be when an electron jumps from the fifth shell to the second shell. Now notice that I got a negative number, and the negative number indicates, that's going to be the next question, is energy absorbed or released? Well, if you get a negative number, that means energy is released. If you want to check yourself, anytime it goes from a higher level to a lower level, it has to give off energy, so you should get a negative number. If it goes from a lower level to a higher number, you should get a positive answer because it's being absorbed. And I do want you to note that if I asked you what's the energy change in an electron jumping from the second shell to the fifth shell, all of this would be the same, except this number here, 0.246, you would end up with a negative number, and so this number would be exactly the same, but it would be positive. So be really careful with your signs, especially in this part where you're doing final minus initial, and what, you know, if you get a negative number in here, your overall number will be positive, which is absorption. If your number inside this parentheses is positive, you'll get a negative number overall, which means energy is released. So in this case, energy is released. Another question, why am I using 4 significant figures for my answer? Well, because I'm using 4 significant figures in the constant that I'm given. I suppose if you started with 2.18 times 10 to the minus 18th, you would do 3 significant figures, but since the energy levels are whole numbers, 2, 3, 4, the significant figures, you want to use as many as possible, but that's why I'm doing that. All right. What is, let's move that up there. What is the frequency of that energy transfer? So there's energy that the electron is, in this case, releasing. What is the frequency of that energy? Again, there are a lot of equations in this chapter that you can use, and I really I'm doing it for you in this video because I really feel like this is the simplest way to go about it. So now, since you know the change in energy, you can use that in the equation E equals h nu. Okay, frequency is nu, h is the constant, which is 6.636 times 10 to the minus 34. And then E is what you just got from the last equation. So if I want to just rearrange this, frequency equals E over H. That's going to be 5.360 times 10 to the minus 19 joules. H is 6.636 times 10 to the minus 34 joules times seconds. So notice that the joules will cancel, and my frequency will be in per seconds, which is the same as hertz. So when I do that calculation, I get 8.077 times 10 to the 14th inverse seconds, or per second. So that's the frequency. Now, one thing you might have noticed is that I dropped the negative sign. Well, that's just really a technicality. Frequency should never be given as a negative frequency because there's no such thing. The frequency is the frequency. So the negative and the positive that you got in the last answer, you always drop the negative, but do keep in mind that this energy is being released. So it's the frequency is still 8.077 times 10 to the 14th per second, or hertz. If it was absorbed, you still have a positive number, so it's just the difference between if it's being absorbed or released. So generally, frequency and wavelength, we don't do the negative number. Okay, finally, what is the wavelength in nanometers of that same energy transition? Well, now we can use, make sure I get that right, we can use one more equation, which says that C equals lambda nu. So that's the speed of light equals the wavelength times the frequency. In this case, we just found the frequency. Let me write that up here. In this case, we just found the frequency. So the frequency, and we know the speed of light is a constant. So let's rearrange this, and I'm going to turn it just a little bit. My high-tech gear here. Okay, so so lambda, which is the wavelength, is going to equal the speed of light divided by the frequency. The speed of light to 4 significant figures is 2.998 times 10 to the 8th meters per second. The frequency, which we got from up here, is 8.077 times 10 to the 14th inverse seconds. So notice that the inverse seconds this time cancel, and my answer will be 3.71 times 10 to the minus 7th meters. Now that's a perfectly good answer. The wavelength of that light, or the energy that's released, which will be in terms of light, the wavelength will be 3.71 times 10 to the minus 7th meters. But notice that I asked for nanometers. Nano means 9, so the easiest way to convert this is to change this to 371 times 10 to the minus 9th meters. So every time I move this over, that would be 10 to the minus 8th, 10 to the minus 9th. So 371 times 10 to the minus 9th meters, which is not proper scientific notation, but for us it works, because then that's the same as 371 nanometers. 10 to the minus 9th meters is a nanometer. So that is, I think, the easiest way to do these problems. I think if you try to do the least common denominator and work all that, it's perfectly fine, and you can get a good answer, but I'm trying to make things as simple as possible for you.